Alright, welcome back to the Kitchen Group Research Channel. Today I'm going to tell you about some work that was accepted in JChem Phys a little while ago. It's been a busy summer on beyond independent error assumptions in large graph neural network atomistic models. This is a collaboration with Zach Ulissi and his group, Hoon and Tian. And so I'll tell you today in a nutshell what this paper is all about. So the gist of this paper is when you do nonlinear regression with, say, any nonlinear model, ideally the fitting errors are independent, uncorrelated, and normally distributed. But when we do DFT, density functional theory, we also have errors, but these errors tend to be correlated across systems. And those correlations lead to error cancellation so that the difference between two energies turns out to be more accurate than the absolute values. Now, our groups have studied machine learned potentials for a while. These are a kind of nonlinear regression. And what we find in this work is that the errors, the prediction errors that we get, show correlations in them. And that enables us to get cancellation of errors similar to what we see in DFT, so that the predicted energy differences are more accurate than is possible for the single ones. So that's it in a nutshell. What we found is the predictions from large graph neural networks that we use are kind of similar in a way that I'll show you to using density functional theory. Okay, so how did we do this? The main idea is that we have a graph neural network. We can give it any one of these configurations on the right, and we can get the total energy. Now we know the total energies aren't perfect, and there are errors in them. But what I just told you is that if the systems are similar enough, then we get some cancellation. So what does similar mean? So we have a couple of different ways of generating differences for different kinds of similarities. So we could have, for example, the same adsorbate on a surface but different surfaces. Those would be different in the surface. We could have the same surface but a different adsorbate. We could have the same surface and the same adsorbate, but on a different site. This would be the most similar. And we could have different adsorbates and different surfaces, in other words, nothing in common. And what we would expect as we look at these different classes of differences, that we see different levels of error cancellation. So that's what we've done. We can swap the catalyst, we can swap an adsorbate, we can look at, over here you see the same adsorbate on two different parts of the surface. And we can look at the differences in energy and see how things change. Okay, we did this with several generations of graph models, going back to Schnet, DimeNet++, Payne, GemNet OC, GemNet OC Large. These are increasingly sophisticated and increasingly large models, and we'll see how this works across that space. And we use some Beef van der Waals as a DFT reference that gives us an ensemble of energies where we can see what's happening. And then we have two metrics to consider. One is what's the error cancellation ratio, that is 1 minus the standard deviation in the subgroup over the standard deviation in the total data set. If these two things are the same, then we get zero cancellation. If this is not the same, then we get some degree of cancellation. So that's what we're going to be looking at. And then the other thing is, do we get the right sign of the difference? Like how often do we get the right positive sign or the right negative sign? These are two things that we've used to compare this. Okay, so if we have independent, normally distributed errors, these propagate in a normal way. So let's say we have an energy here that has some normal distribution around it. We have another error here with another distribution. We can apply standard error propagation rules to say what the standard error in the difference should be. And if we find out that the difference from the GNN is either bigger or smaller, then it means there are correlations that we're not accounting for. And that's what we find. What we find is if we look at differences in the GNN predictions, then we find that the standard deviation does not match what you expect for normal propagation, which implies that there are correlations. And I'll show you in a minute that those correlations tend to go with a metric of similarity. Okay, so we see error cancellation is observed in all of the models. So here we look at this cancellation ratio. A higher percent is better. If it was 100% cancellation, that would be the best. And you see that in the all swap, where there's nothing similar, we don't get a good cancellation of errors because the errors aren't correlated the right way. If we do a catalyst swap, you start to see some. So this is where we have the adsorbate is the same, but the catalyst surface is changing. And that's a big change in some ways, and so we only get a little bit of error cancellation. Same with the adsorbate swap. But once we go to configuration swap, then we start seeing numbers that are quite large in terms of error cancellation, especially when we look at what fraction of them fall into different categories. So the correlation is clearly not perfect, but it's also quite far from random. Okay, the error cancellation we can show quantitatively is enhanced by similarity. So the way the graph neural network works is we have all of these blocks that generate an embedding vector. And the embedding vector is a numerical vector for each atom that describes the local environment, and we can look at an idea of embedding similarity. That is, we can look at how similar are two embedding vectors, and these graphs show that as the MAE goes down, the average embedding similarity approaches 1. That is, they get more and more similar, and the average error goes down. Similarly, over here, the same thing happens for that ratio that we talked about. As you get more and more error cancellation, it tends to happen for more and more similar embedding vectors. So that tells you that when you can show that two things are similar, we expect a higher degree of error cancellation. Okay, so in summary, the GNN predictions are a lot like DFT calculations in the sense that errors are correlated across similar systems, and that means that the differences are more accurate than the individual measurements. Now, it is not as great of an extent as it is in DFT. The GNN errors are much less systematic than they are in DFT, and that probably means there's room for improvement in developing models that are designed to maximize this error cancellation, and that seems like an interesting direction to go with it in the future. So that's it. I hope you enjoy reading the paper, and now you have at least my interpretation of what the main results in the paper are. Thanks. Come back again.